So in this next video in the playlist on real analysis, we are going to look at and prove something called the Riemann Integrability Criterion. Now, this is a simple, easier way to prove that a function is Riemann integrable over an interval within the real line than by using one of the formal definitions for Riemann integration. So in our previous video on Riemann integration, we looked at the formal Darboux definition for the Riemann integral. What we're going to do in this video is we're going to see how that formal definition is equivalent to the Riemann integrability criterion. We're going to prove that, and then in subsequent videos when we need to prove that a function is Riemann integrable, we'll use the Riemann integrability criterion rather than the original definition that we looked at, which was the Darboux definition, just because it's easier to prove the Riemann integrability criterion is met rather than the original definition that we looked at. So let's illustrate this then. So we'll have a function f that is a real-valued function defined on some closed interval ab. And we want to now look at what it means for this function to be Riemann integrable over that interval and see how it's equivalent to this Riemann integrability criterion. So let's remind ourselves of the Darboux definition for this function to be Riemann integrable over that interval ab. So it says that the supremum over all dissections of the lower Riemann sums of f over that interval ab must equal the infimum over all dissections of the upper Riemann sums of that function f over the interval ab. So if those two things are equal to one another, we say the function is Riemann integrable, and then the value of these two things is then the value of the integral of f of x dx from the interval a to b. So now let's write down the Riemann integrability criterion. So the thing that we want to prove in this video is that this is equivalent, so I can put a biconditional there, so the function is going to be Riemann integrable, is going to satisfy this definition if and only if this criterion is met, which is the Riemann integrability criterion. So it says that for all epsilon greater than 0, so epsilon is a positive real number, there must exist some dissection of the interval ab, so there must exist a dissection d, such that if you look at the difference between the upper Riemann sum of the function over that interval with the dissection d and the lower Riemann sum of the function over that interval with the dissection d, it is less than epsilon. So what we have written down here, this is the Riemann integrability criterion. Let's try and understand what this criterion says in a little bit more detail with the use of a picture. So if we have our interval AB here, and then let's graphically represent our function by this curve here, then what this criterion is saying is that there must exist dissections of this interval AB such that the difference between the upper Riemann sum and the lower Riemann sum gets indefinitely small. So for all epsilon, you must be able to find a dissection of this interval such that the gap between the upper and the lower Riemann sum is less than that epsilon. Now remember that the upper Riemann sum over any dissection d is always going to be greater than or equal to the lower Riemann sum over that dissection. That follows just from the definition of the upper and lower Riemann sums. So if I just remind you of what the definition for the upper Riemann sum is. So if we have our dissection d, and let's say it fragments the AB interval up into n pieces, then the upper Riemann sum is the sum from I is equal to 1 to n of xi minus 1, where these are the parts of the dissection. So the dissection, if we write it out formally, will be x0, which is equal to a, which is strictly less than x1, which is strictly less than x2, which is strictly less than ... all the way up to xn, which is equal to b. So these are the cuts that you've made in this interval ab. So x0 and xn are the endpoints, and then all the points in between x1 to xn minus 1, they are cuts that you've made in this interval to dissect it up, and that's what the dissection is. So sum from I is equal to 1 to n of xi minus 1, which is the lengths of the intervals that the interval has been dissected into, times, and then for the upper Riemann sum you want the supremum of all the values of the function over that interval that's part of the dissection. So x is an element of xi minus 1 to xi, and then you want to take the supremum of all values of f of x in that interval. Whereas the definition for the lower Riemann sum is then that it's the sum from I is equal to 1 to n of, again, the length of the intervals xi minus 1, but this time you want the infimum of the value of f of x for x is an element of that interval xi minus 1 to xi. So if you were to expand these great big sums, then each of them would have corresponding terms with the same interval lengths in front of these numbers, the supremum and the infimum, and you'd be able to compare each of those terms, and of course the supremum of the value of the function over each interval is always going to be greater than or equal to the infimum of the value of the function over that interval, and you'll have equality if and only if the function is constant over that little interval that's part of the partition. So combining all of those inequalities together, you then get that this great big sum is going to be greater than or equal to this great big sum. So therefore the upper Riemann sum for the function f over that dissection is always going to be greater than or equal to the lower Riemann sum. Therefore, for any dissection D, if you look at what the upper Riemann sum minus the lower Riemann sum is, which is what we're looking at here in the Riemann Integrability Criterion, this is always guaranteed to be greater than or equal to 0. So what the Riemann Integrability Criterion is saying here is that you can, even though we know that this is always going to be greater than or equal to 0, you can get it indefinitely close to 0, is what we're saying here, because for however small you pick epsilon, if this is met, I must be able to find you a dissection of this interval such that this difference is less than that epsilon. And the dissections that are going to do this in general for a Riemann integrable function will be the dissections that are making every single one of the intervals that you've partitioned this overall interval into smaller and smaller. So there'll be these sort of dissections. So as you make epsilon smaller and smaller, the dissection that's going to satisfy this is going to be one of these dissections where every single one of the intervals is very, very small, i.e. one of these fine, evenly spaced dissections. So let's now prove this, and we'll start with the easier of the two directions. So the easier direction is actually the forward direction, so proving that if this is true, then it implies that this is true, this side of the biconditional arrow. And then after we've done that, we'll do the more difficult direction, which is showing that if this is true, then it implies that this is also true. And once we've got both of them, we'll have shown the biconditional relationship, we'll have shown if and only if, we'll have shown that they're ultimately mathematically equivalent statements. So the forward direction then first, this is the easier one. We get to assume that the function is Riemann integrable over the interval AB because the supremum over all dissections of the lower Riemann sums is equal to the infimum over all dissections of the upper Riemann sums. And we need to show that if that is the case, then the Riemann integrability criterion is going to be met. So if these two are equal to one another, then of course we call their value the integral from a to b of f of x dx. Now we're going to need this value, so I don't want to have to continually write down that big mess, so I'm just going to call this value I for integral. So let's now show that the Riemann integrability criterion is going to be met, and this is actually very easy. So if we draw a real line here, here is the value of the integral, and what we know is that this is an infimum for all the upper Riemann sums. So all the upper Riemann sums are up here, they're greater than or equal to this value, and it's also a supremum of all the lower Riemann sums. So all the lower Riemann sums are down here, they're less than or equal to this value. And we want to show how from this we can derive that there exists a dissection such that for any epsilon greater than 0, the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. So we're going to create an interval then around I such that hopefully the difference between upper and lower Riemann sums is going to be less than epsilon. So the interval we need to take is actually of size epsilon over 2. So we're going to pick this interval from I minus epsilon over 2 to I plus epsilon over 2. Now, because I know I is, let's start with the upper Riemann sums, it's the infimum of all the upper Riemann sums, so it's the greatest lower bound. So 1, it's a lower bound, so all the upper Riemann sums are greater than or equal to it, but it's also the greatest lower bound. So that means that anything that's greater than it is not a lower bound. In particular, this value here, which is I plus epsilon over 2, that cannot be a lower bound for the set of all upper Riemann sums. So that means that there must be an upper Riemann sum that is strictly less than it. And now we know that all upper Riemann sums have to be greater than or equal to I, so that means it's going to be somewhere here. So I will be able to find you an upper Riemann sum that is inside that interval from I to I plus epsilon over 2, not including I plus epsilon over 2. It does include I. It might be the case that it is equal to I, but it's not going to be equal to I plus epsilon over 2. It's strictly less than that. So we'll call that upper Riemann sum the upper Riemann sum over dissection d1 of f. Now we're going to use the exact same argument for lower Riemann sums over here, and then you'll see how we'll know that the difference between this upper Riemann sum and this lower Riemann sum is going to be less than epsilon. So again, because I is the least upper bound for the set of all lower Riemann sums, then that means that anything that is smaller than it is not an upper bound. In particular, that I minus epsilon over 2 is not an upper bound. So that must mean that there is a lower Riemann sum that is strictly greater than it. So we'll show this in green here. So there must exist a lower Riemann sum, which we'll say is over dissection d2, which is strictly greater than I minus epsilon over 2. So it's somewhere inside the interval from I minus epsilon over 2, not including that point, up to the point I. But it could be I. So again, this has to include I. Now, what I know about these two is that they're going to be a difference apart from one another less than epsilon. So we're almost there. The problem is, of course, that we need them to be over the same dissection, and at the moment, they might be over totally different dissections. But how can we fix this? Well, we can take the common dissection, or a common dissection, because there's loads of different common dissections of the two. So this is something that we proved in the video on Riemann integration. One of the things that we had to do was prove something about Riemann sums. We did that prior to actually getting to the definition of Riemann integration. So what we showed is that if you have any two dissections, or actually I'll firstly start with just one dissection. So if we have our first dissection, so let's say this is D1, and let's say we're cutting it up into those four pieces, then if you take a new dissection, which we'll call D bar actually, which is a refinement of that dissection D1. So it's got all the original cuts of D1, but then it's got more cuts, so new cuts, which I'll mark in blue, so it's making more cuts. Then the lower Riemann sums and the upper Riemann sums for this refined one will be better. They will be closer to the, if the function is Riemann integrable, they'll be closer to the value of I. Even if the function isn't Riemann integrable, they will be better than the ones that were less refined. So we capture that with some inequalities. So the lower Riemann sum over the dissection D1, so the unrefined dissection, will be less than or equal to the lower Riemann sum over our refined dissection, which of course will then be less than or equal to the upper Riemann sum over our refined dissection, because upper and lower Riemann sums always have that inequality relationship, and that upper Riemann sum will be less than or equal to the upper Riemann sum over the unrefined dissection. So when you take the more refined dissection, the upper Riemann sum comes down, i.e. it becomes more refined. So remember, upper Riemann sums are too big, so it coming down means it's becoming more refined. And the lower Riemann sum, which is far too small, becomes more refined by getting bigger. So more refined dissection makes more refined upper and lower Riemann sums, and we capture that with this inequality here. So now what we can do is talk about the concept of the common dissection of the two. And there is a concept of the least common dissection, which just means take as few as possible additional cuts that you need to have both of them in, but we don't even need to actually take the least common dissection. We could just take any common dissection. So if we have D2, and I'll mark D2's cuts as, let's just have 3 of them to make it simple. And unfortunately, I've put some of them at pretty much identical points to cuts of D1. But we can actually take this. So let's say that these two are actually at exactly the same point anyway. Then to make a common dissection of the two of them, you want to have all the cuts from both of them in that dissection. So you'd have that cut there that's common to both of them. Then we'd have this cut here, which is from D1, that's supposed to be that one. Now this one doesn't look to be exactly the same as that, so we need to add it on. So we'd have to put it there. Then we'd have this cut from D1, and then we've got another cut from D2. So that's the concept of a common dissection. You have to have all the cuts from both of the two. And the least common dissection would be the one where you've got as few cuts as possible, and you've got all the cuts from both of them. So this would be an example of the least common dissection of D1 and D2. If I was to add more cuts in, these ones in blue, that would still be a common dissection of D1 and D2, but it wouldn't then be the least common dissection. Now, what were we trying to do? Oh yes, so we have this lower Riemann sum of D2 and this upper Riemann sum of D1. What we can now do is create a common dissection of both of them, and we'll call that D bar. And what we now know is that that D bar dissection will give a more refined lower Riemann sum. So in particular, the lower Riemann sum of D2 of F will be less than or equal to the lower Riemann sum over D bar of F, which will then of course be less than or equal to the upper Riemann sum over D bar of F, which, because I'm saying it's a common dissection, will now be less than or equal to the upper Riemann sum over D1 of F. So that's because it's a common dissection of D1 and D2, so it's better than both of them. So the upper Riemann sum over it is going to be more refined than the upper Riemann sum over D1, so it'll be less than it. It will be further in here and closer towards the value of the integral I. And the lower Riemann sum over this refined dissection, because it's a refinement of D2, will be better than it, will be greater than it, because lower Riemann sums are too small. So it again will be closer to the value of I. So now we have one dissection, and we know now that the difference between the upper Riemann sum over this refined dissection and the lower Riemann sum is going to be less than epsilon. So upper Riemann sum over D bar minus the lower Riemann sum over D bar is going to be less than epsilon, because we knew that the difference between the upper Riemann sum over D1 and the lower Riemann sum over D2 was less than epsilon, because they were both inside this epsilon interval around, well, this epsilon minus 2, this epsilon over 2 interval around I. So hopefully you've understood this argument, but I am just going to quickly go through some of the inequality arguments in a little bit more detail. So firstly, let's just talk about where we got this inequality from. So what we know is that the upper Riemann sum over the dissection D1 of F minus I is going to be less than epsilon over 2. That just comes from the fact that this was chosen so that it was inside that epsilon over 2 half interval there. We also know that I minus the lower Riemann sum over D2 of F is also less than epsilon over 2. Again, that comes from the fact that this lower Riemann sum was picked in that epsilon over 2 size half interval here. So from these two things, we can combine those two together to get this inequality here. The way we can do that is by adding this onto both sides of this inequality. So if we do that, the I will cancel, and you'll get that the upper Riemann sum over d1 of f minus the lower Riemann sum over d2 of f. So I'll just remind you what I'm doing. I'm taking this bit here and I'm adding that onto both sides, which by the ordered field properties of the real numbers I'm allowed to do. It will preserve the inequality. So I'm going to get that that is going to be less than I minus the lower Riemann sum over d2 of f plus epsilon over 2. So I've added that bit on to both sides of the inequality and got this. And now what I can do is take this inequality and add epsilon over 2 onto both sides. So I won't bother writing all that out. I'll just put plus epsilon over 2 there. And then on this side I'm going to get epsilon. And then I've got this thing is strictly less than this, but this thing here is the same as this thing here, so I can now apply transitivity. If this is less than this and this is less than this by this inequality, then I can conclude that this is less than this. So that's a little bit more detail of where that inequality comes from. Now let's understand how from this inequality and this inequality I can get that this is going to be true, that the upper Riemann sum over my refined dissection minus the lower Riemann sum over my refined dissection is less than epsilon. Again, I hope it's obvious from the picture, but just to go through it in full formality, justifying it with the ordered field properties of the real numbers, we will do it. So, we're going to split this inequality here up into two separate parts. So we know that the lower Riemann sum over d2 of f is less than or equal to the lower Riemann sum over d bar of f, and the upper Riemann sum over d bar of f is less than or equal to the upper Riemann sum over d1 of f. Now, we want something of this form here, so I'm actually going to take this inequality. We want a negative sign in front of the lower Riemann sum, so I'm going to multiply this inequality through by minus, which will cause me to have to reverse the order of the inequality. So we're going to get that minus the lower Riemann sum of d bar of f, and now it will be is less than or equal to the lower Riemann sum over d2 of f. So that's by multiplying this through by minus 1. Oh, whoops, I've made a mistake. That should be a minus there. Now, remember what we're aiming for. We're trying to get something about this. So that's the reason I've multiplied it through by negative, so that I've got a negative here. Now I'm going to add the upper Riemann sum onto both sides. So I'll have the upper Riemann sum d bar of f minus the lower Riemann sum of d bar of f is less than or equal to the upper Riemann sum over d bar of f minus the lower Riemann sum over d2 of f. So hopefully you can see what we're aiming for now, how this is all going to work. I've got this thing here, and now I've got that it's less than or equal to this. If I could get that this is less than or equal to epsilon, then we'd be in business. So now what we're going to do is use this inequality here. So if we just subtract the lower Riemann sum over d2 of f from both sides, so or add the additive inverse of the lower Riemann sum over d2 of f. So the upper Riemann sum over d bar of f minus the lower Riemann sum over d2 of f is less than or equal to the upper Riemann sum over d1 of f minus the lower Riemann sum over d2 of f. Excellent. So this is all looking really hopeful now, because we've got this thing is less than or equal to this thing, and we've got this thing, these two are equal to one another here, that's the same as that, is now less than or equal to that. So we can now conclude that the upper Riemann sum over d bar of f minus the lower Riemann sum over d bar of f is less than or equal to this thing, and we already know that that thing is less than epsilon. That's what we just showed up here. So now we can conclude, therefore, that the upper Riemann sum over d bar of f minus the lower Riemann sum over d bar of f is less than epsilon. So that's the reason we can conclude that using more formal methods of ordered fields, properties of the real numbers. But the picture also clearly show why that was going to be the case. So let's make a conclusion from this now. So what I just did is, given an epsilon greater than 0, I showed you how you can find a dissection. The final dissection is this d bar, such that the difference between the upper Riemann sum and the lower Riemann sum is guaranteed to be less than epsilon. Now, I made no assumptions about what that epsilon was other than it was greater than 0, so you can actually carry that argument out. It will work no matter what epsilon you pick that was greater than 0. So it is true that for all epsilon greater than 0, you can find a dissection in this way such that this inequality holds true. So if the function is Riemann integrable, then yes, the Riemann integrability criterion holds true. We have proven the forward direction here.